the next session of embedded software testing. This is the lecture 10. This is in continuation of the embedded development life cycle and testing life cycle and different types of life cycle like V model, multiple V model, master V model, etc. So in earlier session we studied about V life cycle. What are the entry and exit criteria that needs to be understood, and what is the dependency, how it's going to enter, how it's going to exit, and we also studied about two types: prototyping life cycle and formal life cycle. And example of prototype life cycle we studied. Just glance through the session what we had in the earlier class. This is an example of prototype life cycle, having entry and exit as a finalized prototype with the finalized SRS, DD, source code, testing aspects, which is enough for going for the formal life cycle. A formal life cycle, we know that it's a V shape. Why? Because on the left hand side we have finalized requirements or specification, then we have a design next to that, then we have a coding, then in parallel to that the various aspects of testing have been carried out. For specification is a high level testing, for design is integration, for coding it is code or unit testing. So that's why it is called V model. As part of the exercise that we do for testing of these levels, we produce the test result. So that is a formal life cycle after we are done with the example, after we are done with the prototyping. So this is another way of depicting the V model life cycle. Each life cycle elements have its own process, like the process have to be having objectives, scope, entry, inputs, outputs, and exits defined for each of the process that we follow life cycle. And in another session we understood about each of these process items, taking an example of test plan, where we identify objective to prepare a test plan, scope is for the project, preparing the acceptance testing, then entry we do with a high level requirement specification, then project plan also is taken care. Then we have the inputs as SRS project plan, outputs as baseline test plan, and traceability. Exit is the outcome of the testing what we do. The preparation is that test plan is the outcome along with the traceability report. Also we went through consumer electronics product life cycle example, and we defined a sample rather general entry and exit criteria for embedded software testing. So testing life cycle we studied it, taking an example of automotive testing, system requirement study, test planning, test execution, and defect management, which also involves test automation, package release, package and release, then the test conclusion or test closure. So each one these 5 phases have its own process. Each of them we studied about its objective, scope, entry, inputs, outputs, and exit. I will not go through in detail because I have already gone through this in detail. As it is applicable in the future, we can address this. This is taking an example of automotive test process, how they follow for testing the embedded software. Also we studied about some of the embedded software words we will touch base this again and again in each class so that we are aware of this. Also, we had a few questions as exercise. So that is about the previous session. Now we will, with that background, we will go through the next session. Okay, we know that V model life cycle how it is. Once we have laid out V model life cycle, there is another variant of V model life cycle that is called multiple V model life cycle. Why this is required? What is the importance of this? Okay, so the essence of multiple V model is that different physical versions of the same system are developed. That means you take an example prototype. We might have prototype 1, 2, 3, etc. So it's a different versions or different feature-wise products as a prototype we will have developed. Each one possessing the same required functionality in principle. That means the minimum functionality has to be there actually, because the end product what we are going to develop is the same, but there will be a multiple variants versions in terms of its physical outcome. This means for instance that the complete functionality can be tested for the model as well as for the prototype and the final product. On the other hand, certain detailed technical properties cannot be tested very well on the model and must be tested on the prototype. That means the end once we finalize the end model, we may not be able to test some of the technical elements of that product. So we may have to go for doing a testing on the prototype itself. For instance, the impact of environmental conditions can best be tested on the final product, but we don't have to do it, or we may not be able to do the environmental condition completely on the prototype. So likewise, we have a scalable or incremental way of having the model used. Testing the different physical versions of this product requires specific techniques and specific test environment. We know that different prototypes will have a different environment. I mean, deviated slightly or as per the need. Therefore, a clear relation exists between the multiple V model and the various test environments. So the system is developed as a sequence of several subsystems development that become more real in the end. So we have a subsystems. It's called multiple physical versions. It is called subsystems. Usually these are model, prototype, and final product. It could be anything what we develop. So the multiple V model based on the well-known V model, it's also called Spillner 2000, is a development model. That means though it is called as a what is that called life cycle elements, requirement design, coding, testing, all together it is called as a development model. The fundamental multiple model is based on the V model in principle. So each of the product appearance follows a complete V development cycle, including design, code, test activities. That means we have a different variants of the prototype developed as a multiple V cycle. So that is why it is called as multiple V model. This is typically used in production environment where they may not be able to conclude on the final end product, or they might not have designed in such a way that one go they will develop the final product. What they do is they will first identify the basic V model. In that again they will identify subsystem V models. So all these subsystems V model comprise into multiple V model life cycle. So this is a master plan sort of a thing. We will definitely study about a master test plan maybe in the next session. Okay, so this figure you can see how it looks like model V development life cycle. We know that we have studied one V in the earlier session. It could be for a model, or it could be for a prototype, or it is for a formal one. So each one has design, source code, development, and build, and testing, design, build, test, design, build, test. So you can see 3V's here, 3V models. One is a smaller one, and the medium one, bigger one. So it doesn't mean that it is same actually. It can have different aspects, like we might have a detailed design or low level algorithms and all the stuff taken care in the bigger one, and the smaller one may not need. It again depends on the what sort of development we are going to adopt. So basically the model or the initial prototype will have a smaller V model life cycle, whereas the prototype will have mixed. So I have put yes, in that book it is mentioned as yes. Why? Because there could be multiple prototypes. Having feature set 1 in the first prototype, and first prototype having a feature set 1, second one having a feature set 2, third one could be having a feature set 1 plus some changes, or you can call it as set 3. Both could be having feature 1, 2, 3 partially, etc. So all this can be there part of the prototype. So we can add multiple like this. So I just drawn now. So in between it can have a multiple V models before we draw on the final product. So that is the meaning of this multiple V model life cycle. Again tell that it will be having multiple development life cycle defined for each of the variants. Like we have an initial prototype defined as a model. It's offhand work basically before we finalize the feature set. Prototypes something like the users will develop a proof of concept application or feature, like feature set 1, 2, 3, etc. And accordingly we will have a life cycle for that also. All this together we will try a bigger V model, that is as a final product or a formal visual life cycle we can call. So this also can be part of a, usually this will be part of a master plan. You can call this as a one single V having multiple V's. That's why it's called multiple V model life cycle. Okay, so in multiple V model life cycle, we have testing activities defined as below. It's basically divided into 3 categories. They are test techniques, test levels, and types, and other issues. Test techniques, test level, and types, and other issues. So these 3 categories basically we divide the V model test activities. Each is then put in one or more V's at the relevant stage of it. That means basically we will identify all these categories, then we will apply into each of these. So that is how it has been done for a test cycle. So we will study about each of these 3 categories. So you can see this table: techniques, test levels, types, other issues. This is actually this whatever I am referring on this model, V model, multiple model, and in the next slides I have nested V models. These are all basically derived from the Testing Embedded Software book by Bart Klockman and Edwin Nordbaum, because there are several techniques and several other concepts that are all used. But this is a book that is being referred for this course, Embedded Software Testing here. Okay, so test related activities and the issues that need to be allocated throughout the development and testing life cycle. What are those? Here development and testing, why we specifically mentioned this, development also can be having some of these tests, because developers as a tester is very important for embedded software testing. I will explain that in a separate slide. Developer as a tester, how it is. Techniques. So what are the techniques that we have that should be considered for multiple view model? This is specific to multiple view model. Code coverage analysis, control flow testing. Okay. Flag and inspection, failure mode and effective analysis is also called as FMEA. Fault injection, faulty analysis, formal verification, interface testing, model checking, mutation testing, random testing, rare event testing, simulation, state transition testing, statistical research testing. These are the techniques that are used or can be considered. It need not be all, some of this based on its applicability, and corresponding test levels or types where they can be applied. For example, code coverage analysis can be applied for design verification, control flow testing, code review. So there is a term called control flow. It's not very clear, so change the color. For control flow and data flow, so some of the very important items that we need to be knowing for embedded software testing in order to understand. Control flow is basically the controlling of the way how the program is controlled. The embedded software product is getting controlled in terms of the logic or flowing down the entire system. Data flow is where the parameters of the data, how it is getting flowed down throughout the structure. So flag and inspection, it's a type of inspection method. Maybe we will discuss this some detail later. For conformance test, we follow this. FMEA for design verification. Fault injection, where we have integration, we inject signal errors or any data errors in terms of system, and we do the integration. Similarly, FTA fault analysis, like this involves the host as well as target. Here, what we do is we do an analysis of the fault. So, what is the root cause of a particular fault in terms of where it's going to hit? That means, if I inject an error, where and all is going to impact. There needs to be analyzed. So again, is the requirement. Definitely, requirement will take care of the fault recovery and fault detection and recovery mechanism. All this will, all those aspects will be tested in terms of fault analysis. Formal verification, model integration test, interface testing, field test. Then we have model checking with regression test, requirements verification, software acceptance test, integration, system acceptance, system integration, unit test. So these are some of the test levels or types. So based on the type of product that we use, these test levels types corresponding to the techniques we can use it. And we have other issues as third category: architectural design, certification, detailed design, detailed test plan, design and build tools, design and build simulator, design and build stubs. I will explain about stubs in a later part. Design and build drivers, design for testability. This is one of the very important thing that now almost all industries they are following, especially product companies like Samsung or LG. In the design phase, they will identify the testability part. That means whether this design can be tested. So without that testability, uh, design is not complete, or design will not have foolproof mechanism. So they need to have some sort of a design which will support or help with testing. It could be test hooks, or it could be a test stubs or drivers or a test monitor, whatever it is. And of course we have high level requirements, legal requirements, low level requirements, master test plan. We will touch base master test plan later. Production requirements, release criteria, advice, etc. So this is the third category. So this is a complete master list of three categories. This all need to be considered before we take up the multiple view model. Those techniques, levels, and other issues can fit into any of this. I mean, basically, we need to draw a picture when we do the view model, multiple view model planning. All this have to be considered. So that is the main thing about multiple view model. So now we consider only the first one, model, multiple view model applicability for model. That means what are this? This is an example. Out of this, how much we can draw for the model. So that is nothing but allocation. It is called allocation of test related issues on the development cycle of the model. So low level requirements and verification, detailed design verification, design for testability. So all this will be on the left hand side. So, as I said, the V model is looking like a V shape, and corresponding to these requirements, we have a release criteria, we have a integration, model integration, we have a conformance test, we have a unit test. These are the some of the selected techniques, test level types, and other issues. So for this, so what is the outcome? Like we have a simulation, we have a area testing, state transition testing, model checking. These are some of the activities. Similarly, on the left hand side, we do FMEA, FTA, formal verification, par inspection. So this is falling outside the wheel, on par with the model. So this is the applicability how we are going to draw based on this master table. Okay. Another one is V model applicability for prototype. What are the categories that we can use for prototyping V model? Here again, outside the V, we have techniques in terms of FMEA, FTA, fan inspection, code review. Within the V, we have low level requirements, detailed design, plus verification requirements, design for testability. Then on the right hand side, we have unit test. At the bottom, host target based testing. We have software integration, software acceptance. Then we have hardware software integration. Then we have system integration. Then we have the package and release on the right hand side. So this can go for multiple testing based on that bug fix and all that with the help of regression testing. And also we, as a result of that, we come up with the coverage analysis. It means how much we are covered, what is left out, what is pass, what is fail, etc. As part of the code coverage analysis. Statistical usage testing, mutation testing, fault injection, data testing, rare event, interface testing, simulation, state transition testing, control flow testing. So this On the right hand side is all about the techniques what we apply for this prototype. This is an example of prototype V model when it comes under applicability under multiple V model life cycle. Final product, the formal product, how we can apply the multiple V model. Product requirements, that means end product requirements, detailed design, and because code and all we already taken care in the prototype. So final product we leave with only the requirements and design. And in terms of releasing or deploying the product into the customer, we have a release criteria, acceptance and all that. Certification is important, especially the products are going to be fitted in terms of safety aspects that needs to be taken care. Certification, like we have DOMS and B from designated authority from Airbus or Boeing. Automotive we have AUTOSAR certification on par with this certification process. And in terms of the techniques, statistical user testing, random testing, rare event testing. So this will be applied before we complete the V model. This is allocation for final product or the formal product applicability. So that is about multiple V model, where we have initial prototype, final product have been organized into multiple V models, each one having design, code, test, design, code, test, and finally we are going to have the final or the formal product, and its applicability is drawn based on a master list of techniques, test levels, types, and other issues. Okay, the next one is nested multiple V model. We have studied about a V model, we have studied about multiple V model, then another term called nested multiple V model. The name itself tells the multiple models are nested basically. Definition is here. When the V model at the system level is combined with the multiple V model at the component level, it results in the so-called nested multiple V model. So the meaning is that system level we have a V model, it is combined with multiple V model. We have seen in the previous slide having prototype, final, and before prototype we have initial one. So once this is combined at the component level, so we have defined the system level. The component level, these multiple models it can iterate. So it is so called nested multiple V model. So we have an example here. You can see this is a multiple V model 1, multiple V model 2, n, etc. So component 1, component 2, component n. This is nested under the one V model. So this is an example of how one example of taking a component as a multiple V model at the component level. So parallel development is also called as parallel development phase V model. So okay, in conclusion of that, the nested multiple V model, all test related activities and issues can be allocated to the correct level in the correct place. That means whatever we identify in terms of testing activities should be applied for the particular level, like component 1, component 2, component 3 specific tests will be applicable for that specific V, whatever we have followed within that multiple V model. So at the system level, higher level test issues can be allocated. Overall development life cycle. There is one more figure 3.7, I think. Okay. We have seen parallel development in terms of V model, component 1, 2, 3, etc. are done. When it comes to nested multiple V model, at system level, test related activities can be allocated to the correct level. Therefore, for this actually, you can see in the bottom detailed test plan, legal requirements, design and build tools, emulators, stuffs, etc. All this will be underneath. That means this is common. Same thing is going to be applied for V model 1, V model 2, V model 3. So as an example, 3V you can see that each V at a system level or component level is replicated again 3 times you can see. So high level test issues in the nested multiple V model as an example is taken care here. That means we have a master test plan, safety plan, we have release applicable for all this as a bigger V model. So when it comes to the individual V model, this portion is taken care of in a nested manner. Same thing is depicted in a simpler way here. This figure 3.6. The multiple V model components are put together. When it comes to high level test, the common line is drawn basically. So the multiple V model with the 3 sequential V cycles, what we have seen, does not take into account the practice or functional decomposition of the complex system. The development of such a system starts specification high level, followed by an architectural design phase where it is determined which components, hardware or software, are required to realize this. And those components are then developed separately and finally integrated into a full system. In fact, the simple V model can be applied to this development process at a high level. The left side of the V model handles the decomposition of the system into its components. The middle part of the V model consists of parallel development cycles, what we have seen here. For all the components. The right side of the V model handles the integration of the components. So I repeat this. The left hand side of the V model handles the decomposition of the system into various components. As we said, high level requirements, design, low level design, coding, etc. The middle part of the model consists of the development cycles, like we have a prototypes 1, 2, 3 are components parallelly getting developed. On the right hand side, we are going to have a validation or integration of all activities, all these aspects. So this principle can be repeated for components that are too big or too complex to develop as one entity. For such a component, an architectural design activity is carried out to determine which subcomponents are required. We need to have an architectural design, so that will identify how many subcomponents are required to make the system working. So this also could result in another V model. Within the V model, we can have another V model. So that is why it is called as a nested V model. Okay, so multiple V model is not only helpful when it has to be planned and executed for a completely product, but also in the case of new releases of an current product. So in fact, the development project for a product is about the new release of just a few components. Then the multiple V model and the full or the master plan related to the development of the complete product can help to identify the relevant test activities. So basically, when we have a complex or bigger systems, what we do is we go with the parallel development of different V phases. And as I said, on the left hand side we have divided basically into components. We identify the system into multiple components. So the middle part will identify the cycle for each of these components, and the right hand side we will have the integration. I'll just type it. So on the left hand side of the multiple or nested V model, what we have is both decomposition into subsystems or components. The middle part we have the parallel development cycles of each of the component for each of the each components. On the other side we have the integration of all these subsystems components. So that is the significance of multiple view model in context with the listing. So basically this is used in bigger or complex systems where we have numerous features identified for numerous components. So that is the significance of multiple view models applicability in terms of nested nature. Okay, having understood these models, different types and their activities categorized, now we move into the testing aspects, irrespective of whatever the model we follow, etc. So we know that host and target are available for both the test team as well as the development team. So now taking into consideration how testing can be done by developers, how testing can be done by independent test team, and there are a few principles that we need to go through. We will go through in the end. Okay, testing by developers. So we know that systems are developed by larger teams, sometimes divided into teams into multiple allocated subsystem teams, or it could be physically separated. We know that bigger systems or complex systems like car embedded systems or aerospace embedded systems are not developed at one site. It will be geographically separated, though they have an interconnection and all that. The team, the testing environment, or the components, or the lab, and all that will be separated. So the developed systems are large and complex, and that alone puts quality under pressure. That means all should work in tandem. Make sure that they work for the quality and the end result that is intended for the product. The demand for quality is increasing because of the competitive market or the use of systems in safety critical situations. So two aspects. One is competitive market because there are several vendors or developers available. So we need to come up with a good quality. Also there is a safety aspects taken care. So in order to avoid all these things at a later stage, so better to do a testing little thoroughly in the starting stage or the beginning stage. So beginning stage we know that there will not be any active testing or formal testing, though there are test plans and all that. So the best way to do is testing done by developers. So that is the background of why testing we need to have it by the developer. So what are those? The existence of an independent test team does not mean that testing during the development stage is less important. That means it is equally important to have a testing done at the development time. Both teams have their own important role in the preparation of an end product with the desired quality. It means they have their own role, testing team, the independent test team, whereas the developers as a tester have their own uh, responsibility. So the end product should be having a high quality. That is the desired goal. And independent testing in general executes tests based on the requirements, and their purpose is to provide confidence that the system fulfills those requirements. So they go by what you have specified, what the product is supposed to do, what you have documented, what you have specified in the requirements. They just go by that. Whereas in contrast to that, the developers start testing at unit level because they are very near to the unit and they are the owners of the unit because they have developed, because simply they own it and they are having the knowledge. That means they know about the infrastructure of the software. This knowledge is used again to test the integration of the different units for the purpose of delivering a stable system. So what they make sure is they develop the unit, the piece of software, and since they are knowledgeable, they use the same test bench or the develop or debug environment to test it in terms of unit level or in terms of integration level. To address two things, one is the quality, so that there are no bugs creeped unknowingly. Second thing is the system that they developed should be stable. So those two purposes are attained with the help of doing the testing at the early stage. So that is why we need to have a testing by developers in the early stage of the development. So continuation reasons why testing by developers is important. Early detected defects are usually correct. In general, the cost of fixing defects will rise in time. We know that we have seen a chart where the cost rises as we go deep into the product before we release the product. So we cannot afford to have bugs or issues at the end stage. It's expensive. High quality basic elements make it easier to establish a high quality system. That means the basic elements you put it right in the beginning only, so the end product, the whole product will come good. Low quality basic elements on the other hand will lead to an unreliable system, and this can't be solved practically by functional tests. It means uh, you would have creeped some quality issues small into different elements in the beginning. In the end, it's very difficult to detect some of the bugs that got introduced because of the low quality during the development. Defects detected during post development stages are difficult to trace back to source. As I said, we cannot afford to have small defects during the development stage. It's very difficult to trace it back. So better to identify in the beginning one. Defects detected during post development stages have to be corrected, and this will lead to time consuming regression tests. That means we need to have a regression again and again, because the fixes that have been done on the product have again need to be tested. Good testing during development stage has a positive influence on the total project time. That means we have the confidence, we have the predictability, reliability, etc. done in the end stage because of the good testing we have done in the development stage. State testing of exception handling is only possible at unit level, where exceptions can be triggered individually. I will tell about exception and interrupts sometime in the later stages because this is a new system development world, you may call it as an interrupt as a result of exception. So exceptions are somewhat unknown behavior of the system under certain conditions. At the unit level or the source level, it may be difficult at a later stage, better to fix at the development. So it may not be possible quickly to do it testing as well as fixing at a later stage. So that's why we need to have some sort of testing done at the development of the product. That means basically quality may not be or cannot be added to the product at the end by testing. It should be built in right from the start. Checking the quality at every development stage is very much necessary. So how we can do is by testing. So testing is not pursued by any developers as the most rewarding task during development. That means developers I have seen ignoring test aspects. They will never care about testing aspects. So the emphasis is to have a testing thinking, testing the thoughts while doing the development. So to keep that test effort for developers at acceptable level is a good practice. It should be effective and efficient. To do this, an integration strategy should be chosen. That is, development also will have some sort of integration strategy. Integration strategies are we can we have anyway we've seen some of the integration strategies earlier. Maybe we can go through that again sometime in the next sessions. So essentially, all activities have to be planned and should be controlled. So that is the fulcrum of testing by development stage. Testing at development stage. Okay. Now testing by independent testing. We all know that testing is an important aspect. There needs to be a testing plan, testing procedures independently getting done by a separate team. We have a test plan also. So we'll just go through that. What are those testing by independent testing? Independent test teams are mostly occupied with the high level test. As I said, they go by the high level test having requirements or specification identified as input. These tests occur at the end of the development test life cycle. We know that development life cycle is getting closer. The testing activity will start. The test activities of these teams are on the critical part of the development process. That means it's very important element in the critical path. It's an critical path. It's a item that is under the critical path of the whole life cycle. The supporting activities have the objective of keeping the time needed for test execution to a minimum. It means whatever the supporting activities we need to have, they have the objective of keeping the time needed for test execution to a minimum. That means when we are doing the development, we identify the test activities and planning. So we do small test hooks and all that as a support. The objective is we will have a predictable time, how much it is needed for test execution, at least a minimum how much it is needed for each of the tests. So that is the idea behind supporting activities. Supporting activities are kept outside the critical path by executing them in parallel with the development. As I said, support activities like test books development, identifying the strategies in parallel to development are all taken care as a separate activity supportively for development as well as testing. So this will not be a critical path, but it's used while testing execution or actual testing is happening, which is under critical path. Formal life cycle for independent testing. Basically, what are the life cycle items or phases for independent testing is explained here. planning and control phase, we have preparation phase, we have specification, execution, completion. This is basically different phases that is been mentioned here. These are all mapping to what we have discussed in earlier classes other way. But in terms of formal life cycle for independent test team taking requirements as a input and doing the high level test is they have to plan and control, they have to prepare, they have to specify, they need to execute and complete it. So these are the phases that are used for independent testing. Okay, this is basically a formal what is described here. Because here this involves many stakeholders, including the test management and development lead also will be involved because he needs to know what bugs, what he needs to fix. So what is the test, how it is getting passed or failed. So most of the information needed by the test team should be provided from outside the test team. That means whatever they need on the product should be provided. And each stakeholder has its own objective and expectations as a testing. Sometimes the outcome of the test process is subject to an external audit. That means there is a separate audit that is taken care against what is being specified. So there is an audit team or the independent team who does audit on test team also. Is an important thing actually. I think I can mention this. Independent activity to audit the adherence process against what is specified in plan or specification of the test aspects. So this audit can happen on any aspects of the life cycle. It can happen on the test management. Audit can be done on the test management, development team and their activities, quality, etc. Don't get confused with audit and quality. Quality is a different thing. Audit is a different thing. So these are some of the formal life cycle aspects that are used. Okay, so that is about testing by developers, testing by independent team. Now we will move on to 10 principles of embedded software. I think I'll take up this in the next session as we are running out of this session. So I will go through the words which we have done before as well as today. So we model a couple of words I would like to add: control flow, data flow. Then what is that we have is audit. So anything is needed, we can add it. Test harness, test bed, test bench, ATE, model based testing, test steps, driver, fault injection, MCDC, test hook, boot software, bootloader, input output, ICD, breakpoints, emulator, trace, profile, datasheet, errata, ICE, in-circuit emulator, test equipment, code checker, static analytics, dynamic analytics, disassembly, reverse engineering. We have life cycle, entry and exit criteria, baseline, prototyping, stakeholder, V model, control flow, data flow, audit. Anything that we want to highlight, we can do it. I think we have taken care of all this. V model we have listed out. Okay, so that is about some of the words. Why these words I am going through each session is to have this in mind as a tester, so that we will not forget. This will be part and parcel of the embedded software tester. That's why it is important to have this. Okay, so we have a couple of questions for this session. What are the differences between V model versus nested V model, multiple V model? So list out a difference between a V model, a multiple V model, and nested V model. What is the significance of nested V model? So why we need it? So we have discussed about this. Please answer these questions. So that is about this session. Next session we will see the next aspects of software testing.